Hi, everybody. Okay, so then now that we have the matrix of a transformation relative to bases, we can talk about the inverse transformation. Now, if you remember, I gave you a way to determine whether a linear transformation had an inverse. It just needs to be 1, 1, and onto. But I didn't show you how to find the inverse. There's a good reason, because it requires the material pretty much that we've just gone over. So suppose you have a transformation that goes from vector spaces U and V that are both finite dimensional. And suppose they have bases of B and C respectively. So then the linear transformation T is invertible if and only if the matrix of T relative to the bases B and C is also invertible. That's a really neat result. And in fact, not only is the linear transformation invertible, but if it is, then I can even tell you what the standard matrix of the inverse is. The standard matrix of the inverse transformation from C to B is the inverse of the matrix of T from B to C. It's really neat. So the reason why is not difficult. It's just a matter of using the composition theorem that I just gave you about two transformations and just being clever about it. So suppose, for one, that T is invertible. That means then instantly the dimension of U and V have to be the same. So we'll say they're N. Why that's true is not hard to see, because if T is invertible, then it must be 1 to 1 and onto, which means instantly it's an isomorphism, which means that U and V have to have the same dimension. That forces then that the number of rows and columns for these standard matrices are the same. So the standard matrix for T and the standard matrix for the inverse of T have to both be N by N matrices. Next, remember that their composition is the identity. So then this is just the mappings. I can find these functions, these separate mappings relative to the bases. So since it's the order of T composed with T inverse, that means then that both sides are going from V back into V. So because of that, I can find out on both sides what the mappings are, what their matrices are, relative to the standard basis, relative to the basis of C to C. But the left-hand side then is a composition, and I want the matrix for it. Because of the theorem I just showed you, I can then show that that's equal to a product of two matrices, which is the matrix of T from B to C times the matrix of the inverse from C to B. Notice how the inner ones are B, so they line up. But the matrix for I relative to C, I showed you that already, that was the identity matrix. Okay, well, this is then the product of two N by N matrices that equals the identity. We know from a previous theorem that those two matrices are both invertible and one's the inverse of the other. And that is the result that we had to give. Let's go ahead and take it for a spin so you can see how this could be used. So we already know, if you recall, the differential operator on the space S, which is the span of e to the 2x, x times e to the 2x, and x squared times e to the 2x. And I've already shown you that the matrix of D relative to the basis B is this matrix here. But because of that, that means I instantly know that D is invertible because that matrix is invertible. And in fact, the matrix for the inverse relative to B is the inverse of the matrix that I just gave you. So here it is. This then is the matrix for D inverse. Now, as an application, as a fun thing, notice how I'm undoing the derivative. So I should then be able to find the integration of 3 times x squared times e to the 2x, because that's the inverse of the derivative of 3 times x squared e to the 2x. So I need to know what that is. Now, using the techniques we know, I don't know what this equals, but what I can do is I can find out what it is relative to a basis, the basis B. Once I know what it is relative to the basis, I can then come back and then I can find out what the vector actually is, because I'll have the coordinates relative to D and I have the basis. I'll have the coordinates relative to B, and I'll be able to find then the actual vector. So the coordinates of the image of the inverse applied to this vector, 3x squared e to the 2x, relative to the basis B. is equal to the standard matrix of D inverse relative to B times the coordinates of the vector 3x squared e to the 2x relative to B. Thing is I know all these things. I know what the standard matrix, I know what the matrix is of D inverse relative to B, and I know the coordinates of that vector. So then all I do is just write it down, and I do that multiplication, and I get that vector. Now that's the coordinates of the result. It's the coordinates of the result. So then if I want to know what the result is, I then just form a linear combination of the basis B using those coordinates, and I get that answer. And that's right. That's actually the antiderivative. That's really neat, right? It's really neat. Now there is something a little wrong. What's wrong is there should be a plus C at the end, and the plus C is lost because the derivative operator limited to this span, I never take derivatives of constants. They don't exist in that span. So I never have to worry about that the derivative of all constants get to 0. In fact, if I look at the derivative operator in general, it's actually not invertible because the kernel is always at least more than the 0 vector. It also involves all constants. So unfortunately, I can't do this in general, but I can in this one case. Okay, now I promised you that the reason that we did all this is so that we can find how to find the inverse. So we already know, though, from previous work, the previous videos I gave you for the previous class, that this particular linear transformation is definitely invertible. To find out what the inverse would be, I'm going to do this. Let's go ahead and use that B1x being the standard basis for P1, and I'll use E1, E2, that's the standard basis for R2. Then you can find out that the standard matrix of T relative to B into C is equal to this matrix. It's 1, 1, 1, 2. Notice that matrix, by the way, that's definitely invertible. So since that matrix is invertible, then the transformation is invertible. So it's not really a question, is there an inverse? It clearly is just because of the matrix. So then if I want to know the inverse of that transformation from C to B, then that's equal to the inverse of the matrix of the transformation T from B to C, which I just know. So I just take the inverse of that matrix. That's the standard matrix then. That's the matrix for the inverse transformation relative to the basis C and B. So it's from C into B. But I want to know what the inverse mapping actually is. Well, so to find out the actual mapping, I'll find out what the image is for a standard vector, for a boring old vector in R2, but relative to B, the basis. Because once I know the coordinates, I can come back and find out what this actually is equal to in general, without the coordinates. So then by the result you've seen, this should then be equal to, it's the matrix of the inverse from C to B multiplied to coordinates of the vector AC relative to C. Well, C is just the standard basis. So AB relative to C is really just AB. It's really just the same thing. So then I just do this multiplication and I get that. That's the coordinates of the image relative to B. So since I know what B is, it's 1 and X, I can then find out what the inverse applied to the general vector AB would have to be. It'd be the first coordinate, 2A minus B times 1, plus the second coordinate, negative A plus B times the second vector in the basis, which is X. That's it. That's actually the inverse. Neat, right? It's a clever way to find the inverse. It works. You can always use this as long as that the transformation is invertible.